Okay, so don't forget, I'm not here tomorrow, but I will have a worksheet for you to look at, as I mentioned earlier. Quiz on Friday, test on Monday the 4th. It's going to be completely over vectors. I'm kind of toying with the idea of just making the test nothing but application problems, like word problems. So kind of see how that works out. Uh, that's all I got, unless anybody has any questions. Okay, then let's see. We started talking yesterday about some word problems. We introduced quadrant bearing and true bearing. We talked about from the horizontal. We worked one problem twice, both graphically and algebraically. And then I asked you to go ahead and try this one on your own. Okay, how many people had the opportunity to go home last night and come up with an answer? Okay, so many hands going up. Okay, well, let's go ahead and work through it together, and let's see if we can come to an answer. While playing a golf video game, Anna hits a ball 35 degrees above the horizontal at a speed of 40 miles per hour with a 5-mile-per-hour wind blowing as shown. Find the resulting speed and direction of the ball. Okay, so let's go ahead and start with the wind. It's going to be the easier of the two. I'm going to start to focus on these algebraically, just like I did on the number 25 homework problem. If anybody has a question about it graphically, just let me know, because I think there was a few people who liked that method. But let's say W represents the wind vector. Okay. Now, what am I going to write for the component form, because it is going due east? It would just be positive 5, what? 5, 0, yes. There we go. Now remember, if it's on the x-axis, okay, the angle of elevation on the positive is 0, so you could still plug in the formula, 5 cosine 0, 5 sine 0, but it's still going to give you the same thing. Okay. Now for the other one, let's say the ball, why don't we go ahead and say B represents the ball's component form. Okay. So how fast was the ball traveling when she hit it? Okay, so 40 miles per hour, that is our magnitude. Okay, so 40 times the cosine of what? Okay, 35. So here I can actually use 35 because it does say with the horizontal. Okay, and remember, these formulas, this one in particular, always takes theta rotating from the positive x-axis. Okay, so it is cosine of 35 degrees. And what? What would be the y value or the b component? 40 sine of 35 degrees. There we go. And let's go ahead and determine what those are going to be. So 40 cosine 35, let's get rid of this real quick. Okay, so 40, okay, cosine 35. So what am I going to get when I push enter here? Okay, so let's say 32.77 or 32 point, 8 if you want to. Let's go 2 decimal places, why not? 32.77. Okay. And then somebody help me out with the next one, 40 sine of 35 degrees. Let's take it to 2 decimal places as well. 22.94, okay. 22.94. Okay, so this right here is the component form of the ball. We got the component form of the wind, but I'm looking for the magnitude of the resultant and its direction from the horizontal. Satish, what do I do? There you go. So the resultant, the vector I'm looking for, is going to be the sum of the two component forms that I have. So remember, we're going to be adding up the corresponding values here. So what is a 5 plus 32.77? Okay, so that would be 37.77, comma. And then the other one plus 0, 22.94. Okay, so this one's key. We now have the component form of the resultant. Okay, this is what's going to allow me to get my answers. And let me take those off real fast. I don't know where those came from. Looks like equals YY. That is not what I meant to do. There you have. Oh, they won't even move now. Delete. Okay. I don't know. I don't even know why they won't remove themselves anymore. Okay, so I'm going to leave them as is. Okay. So what do I do from here? How can I find the actual speed of the ball with the wind? There you go, square root of a squared plus b squared. So remember, in your component form, the horizontal is the a, the vertical is the b. So the magnitude of that resultant vector, square root, in this case a squared 37.77 squared, plus b squared 22.94 squared. Okay. And let's see what that result is going to be. Okay, there we go. Someone already told me, so let's see if I can catch up. So what would that be? Was it 37.77? Okay, squared plus the other one, what was it, 22.94? Okay. All right, so the magnitude of the resultant, or the actual speed of the ball, about 44.2 miles an hour. Okay. And if you look at it graphically, that kind of makes sense because the direction of your vectors, the wind is pushing the ball along, so it's going to make it go faster. Okay, so this right here, what do we say, 44.2 miles per hour. Okay. But now we want the direction of the ball. So this problem gave me the degree measure from the horizontal, so I want to remain consistent. How do I find that? What was that little formula we used? Tangent of theta equals what? There you go. Tangent of theta equals b divided by a. Again, this a and b from the component form of the resultant. Once you find the resultant, all you got to do is apply those formulas. Okay, and you should have everything you need. So I'm going to skip a few steps here. So theta is going to equal the tangent inverse of that ratio. So b was 22.94 over a 37.77. Okay. So let's see what that turns out to be here. So tangent inverse, control divide 22.94 over 37.77. Okay, push enter. So I'm getting about 31.3 degrees from the horizontal. Okay. Does it make sense that we should get a measure less than what we got before? Okay. Does anybody want me to go ahead and visualize it with a graph? You do? Okay. So let's take a look at this. So theta came out to 31.3. Okay. 31.3 degrees from the horizontal. Okay, so let's say we were going to go ahead and take a look at this. Now, we've got two vectors. Let me go ahead and do this in red, make it stand out a little more. So we've got the wind going at, what was the wind, 20 miles an hour? Or no, the wind here was 5, I'm sorry. So I was right, the wind is 5 miles an hour. Okay, so we've got that vector here, and then we've got the ball that's hit 40 miles per hour, but with a 35-degree angle of elevation from the horizontal, right? Well, if you were going to do this graphically, remember, this one isn't already set up, so I'd have to move one of the vectors so that they connect how? Has to be what? Can I go terminal to terminal? Nope, it has to be terminal to initial. So let's say that I go ahead and move this wind vector up here. So his initial to the terminal of the ball. So right here. So that's 5. Well, the resultant that we came up with is this guy right here. So remember, the original one, that was 35 degrees, but now this resultant has a lower measure that we should have found. That's exactly what we got. Also, you can see that with the ball hit, the wind directly behind it, it does increase the speed of it. So it went from 40 to 44 point, what was it, 2? Okay. How are we feeling about the word problems? Okay. They pretty much remain consistent, okay? As long as you find the component forms of those vectors, you're going to be just fine. Okay, so speaking of, let's try another one. Okay, so we got a, now that's off. Maybe I can get rid of it. I'll do it later. Okay, so a charter boat leaves port on a heading north 60 degrees west. Okay, so let's say that port is the origin. Okay. What bearing is that? Is that true or quadrant? That's quadrant. So in fact, what quadrant would the ship be in? Okay. So north 60 degrees west for 12 nautical miles. So the distance here is going to be my magnitude. Okay, nautical miles. The captain changes course to a bearing of north 25 degrees east for the next 15 nautical miles. Determine the ship's distance and direction from port to its current location. So just like before, okay, if my measurements are given in this case quadrant bearing, I want to make sure that my answer is going to be in quadrant bearing. Okay, so who thinks they can come on up and help me with this? Right now, I just need to get the component forms. Let's go ahead and say that the first distance the ship travels of 12 nautical miles, let's say that's u. And then when he changes direction, 15 nautical miles, let's make that vector v. Okay. All right, so I'm not seeing any hands go up. That's okay. I've got the random number generator pulled up right here. So no volunteers. Okay. 5. Ethan. All right, so thank you, Ethan. Appreciate it. So all you need to do, you're not solving the problem. I just need the component forms. Okay, so there's vector u. Okay, so there's vector v, 25 degrees northeast, 15 nautical miles. Okay, now remember our formula, as long as we have two items, the magnitude and the direction angle, we can get the component form. So do we have everything we need? Now, it's not 60, though. Not in this case. Because remember, that formula always has theta starting where? On the positive x-axis. So see, I went 60 degrees left of true north. It would be 150. There you go. So 12 cosine 150, comma. And let's go ahead and move that over a little ways, because otherwise we're about to hit the graph. There we go. So 12 cosine 150. Sine 150. Okay, and that's a component form for vector u. Now we want to do the same thing for v. What's his magnitude? Now that would be theta. 15. Okay, there we go. That's the magnitude. Cosine of 65. Good. (15) sine of 65. Perfect. Okay. Now let's revisit it. Is everybody okay why we chose 150 and 65? Is there anybody who is not sure why we've got those? Okay, then from here on, it's just a matter of getting the decimal equivalents. So I'm not going to bother going over to mine just yet. I'm just going to go ahead and plug in. So I'm going to take this first one here, 12 cosine of 150. I'm getting negative 10.39. That what you guys are getting? Okay. So let's say this is U, this is V. So let's go ahead and approximate them. So negative 10.39. That was 12 cosine 150. So somebody help me out. I need 12 sine of 150. I'm getting 6. Okay. That makes sense because that's 1/2. Okay. Then V. All right. Now I want 15 cosine of 65. Skylar, what are you getting? Okay. So let's say 6.34. Let's keep it consistent here. All right. And then 15 sine 65. Let's say, Jane, what'd you get? Okay. So let's go to Fawaz. Oh, you got it? Okay, let's say 13.6 on that one. Because that one was 0.59. 13.6. Okay, perfect. All right. So is anybody having any trouble finding the component forms of the vectors in our problems? Is everybody okay with this? Okay. Well, now what do I do? How do I find the resultant vector? We add them up. Okay. So the resultant vector would be u plus v. Okay. So I'm going to go ahead and add these up. Let's see, that plus. So for the first one, I'm getting negative 4.05. Negative 4.05. Okay. And then now I want 6 plus 13.6. That one's easy enough. 19.6. So is everybody okay with that being the component form? Okay. Now, here's the thing. In order to find the magnitude, the distance that the ship is now from port, what's the formula again? Okay. So the magnitude is the square root, a squared plus b squared. Okay. So the square root, remember a and b are coming right from this. So negative 4.05 squared plus 19.6 squared. And that should give me the number of nautical miles that the ship is from port. So let's see if this works out nicely. Okay. Control divide, parentheses. What was it? Negative 4.06. Was that right? Squared plus 19.6. Oh, was it 05? Okay. 5. And then 19.6. What was I off on that? It is 19.6? Okay. So I'm getting about 20 nautical miles. Is that what you folks are getting? Okay. So it is 20 nautical miles from where it started. Okay. I'll just go ahead and put NM. I don't know what the abbreviation is for nautical miles. Nanometers? Okay, well, there you go. It's all ship shape. Okay. See, I was going to make another joke, but I didn't know how people would react. Okay. You know, on this problem, the ship is about to hit the fan. I did say ship. Yeah, I'd make another joke, but it'd be pretty crappy. Okay. Now, how do I find my direction angle? We use tangent. Okay. So are you noticing a consistency in these problems? Tangent of theta is equal to b divided by a. So theta should equal tangent inverse of 19.6 over negative 4.05. Okay. All right. Now, here's where it's going to get interesting because you have to think about why you're getting the answer that we are here. When you take tangent inverse of a negative ratio, it's actually putting you in what quadrant? It's actually putting me in quadrant 4. Okay, so let's go ahead and see what this is first. So tangent inverse, okay, this ratio, what was it, 19.6? Oh, yeah. 19.6 over the negative 4.05. Okay. So negative 78.3, okay? So let's say this is right here. I'll just go ahead and put 78.3 degrees because remember it has to rotate from the standard position into that quadrant. But we know, especially if you were to do this graphically, the resultant is going to end up in quadrant 2. So you may have done this similar on your homework for a few problems if you decided to do it this way. If I go ahead and extend the line back over here, then this would be 78.3, right? Okay. Well, what I'm looking for is this measure right here. So how can I find it? Subtract from 90. Okay, that's exactly right. So I'm going to go ahead and take 90 minus the previous value. Oh, and actually let me go ahead and take off the negative because otherwise it's going to, whoa, that was weird. So 90 minus, okay. Because otherwise if I hadn't taken off the negative, it would have added it and given me the wrong one. So this is what I'm looking for, about 11.7. Because remember, we were looking for our answer in a quadrant bearing, right? Okay. So, Connor, how would I write that? Knowing that I have 11.7 degrees. So the ship is 20 nautical miles from port at what quadrant bearing? Okay, so I'll say 7 degrees west. There you go. Okay. Questions? Okay. All right. So we will continue this on Thursday, and we should be able to pretty much wrap it up. Okay, good. Good, 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 good. Interesting. Choo, 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 choo.